The delay is fascinating. The delay is fascinating. Okay, well, might as well stick with what we normally do in class, and I'll start just before on time. This is a practice session. I'm going to talk a little bit about my research, become a little more comfortable with the tools I'm using to record, and yeah, give my students an opportunity to learn more about what we do outside of the classroom, specifically looking at how we design sustainable materials, which is a very broad topic. So let me start. My name is Julian Silverman. I'm an assistant professor at Manhattan College, and I have been tasked with teaching online for the rest of the semester. And so I was going to practice a little bit by talking about my work, what led me to the courses that I teach today, and also what interests me beyond grading wonderful exams and answering student questions. So the goal is to practice not only using the physical materials that I have, but the software as well. So this is my first time really using Twitch, and so far so good. Later today I'll be practicing a little bit with an above head camera, so I can also write out equations and do some work. But today we're going to keep it easy and just look at some of the different examples of sustainable materials that I've worked with, and how we can balance the safety and sustainability of the materials that we use. I'm also going to practice not saying too much. So let's do it. Today we're going to specifically talk about how we can have sustainable resources or ingredients from biomass to make different materials. And I guess we'll describe materials here as really anything that's not an individual chemical. It could be mixtures of chemicals in liquid or solid states. Yeah, and we'll talk about what makes them functional too, useful, and having them be able to be applied to different things. Lastly, a little bit of theory. What we do is we step away and we critically evaluate how sustainable our resources were, how safe our materials are, always balancing the two ends of that spectrum. And we'll do this using what's known as a life cycle assessment, which is really just a fancy pre-lab that you can use to determine the types of materials that you're working with, here referring to ingredients, I guess. Also, the methods with which you process those, which is to say you could heat something, you could microwave it, you could do some redox, things like that. And then also, yeah, just beginning to be careful about how we analyze and evaluate things and come up with different impacts that relate to the society, the economy, and then also people and efficiency. And so we'll look at all of those. Just a little bit about myself. So my background was in atmospheric and environmental chemistry at McGill University. So there I learned a lot about catalysis, both in the atmosphere and also doing materials research. From there, I did my graduate degree focused mostly on looking at the applications of the materials we were making, and that's where I started to go from the inorganic world of nanoparticle catalysis to the more bio-based or biomass-based processing, and I did some biocatalytic reactions as well, so looking at catalysis from different sides. Then I moved over to Kansas to work during my postdoc, mostly in the engineering departments, looking at making sure that the processes we use to make these sustainable materials and chemicals are actually realistic and scalable as well. And outside of the traditional science, I also have a background in assessment design and some education work, specifically looking at open educational resources, which is exactly what we're exploring here today. My background is in actually spreadsheets, which is not as exciting as video, so I'm excited to be exploring this avenue as well. Last but not least, all the other nitty-gritty stuff that comes with being an academic and also just a person, right? Asking for money, reaching out to other people and sharing your message, making things look bearable, and talking, just conversing. And so all of these kind of make up what I think are my most useful and practical skills, specifically also within the context of research. So let's jump into it. Today we're going to talk about not only where we get sustainable ingredients for our materials from, but also the processes we use to transform those. So you notice three main components here. We have the stuff going in, the feedstocks. We have the platforms, which will be used to transform these, or the methods. And then we also have those products. So you can think about something being transformed into another product. And the general categories for each of these include plant-based resources as a feedstock. So this is going to be in battle with food versus fuel, right? You don't want to take away too much corn for your gasoline or ethanol, but you also want to make sure that you have the neat, cool chemicals that you need to work with, fats and oils and aromatics and things like that. On top of that, we also have lots of waste, which is my specialty as well, looking at things that people get rid of for free and turning those into valuable and viable things. And then compost, I guess, could be considered a form of waste. But really, actually, it's interesting to think about how compost is not waste, right? We're going to reuse it, and so maybe we can think about all of our waste as a form of compost or something that's going in transition to the next feedstocks. So those are what we put in. We also look at what we transform them with. In this case, we could distinguish between, say, a biochemical transformation like a fermentation versus a traditional thermochemical, where you might use a whole organism, maybe not just I guess that's biochemical as well, but you could use, say, for biochemical, a protein immobilized on a bead or something like that. That's a little bit of what I did during my grad school. And then lastly, we look at the products. We look at the stuff that we already know and love that we need to replace with renewable feedstocks. But we also need to look at products that we haven't invented yet that are even cooler or go a step beyond where we are today. And so examples include things like fuels, also materials, which is what I will focus on, and then generally just chemical production methods. So a little bit of what I did in my postdoc. And so the first question would be, why would we use waste biomass? So waste biomass could be anything that you're generally not consuming, say like the rinds or the twigs or the leaves. And we know that in each of these distinct components, there are a variety of chemicals that are very useful. For example, things like carbohydrates in, say, the long polymeric chains in your leaves. You also have a different type of polymer in, say, the bark of different plant species, of all vascular plants, I believe. This is going to be in the form of lignin, which is a variety of aromatics. And then we'll also look at, say, the oils you can get from your seeds. And so without sacrificing food, the question isn't why would we use waste biomass, but why would we waste biomass at all? Everything can be either composted or transformed into something else. And so I'll go through some different examples with each of these components today, and also how we combine them to make valuable materials. So the way that I did this in my PhD was pretty much trial and error. What you do is you take, say, two different components, maybe a fatty acid or a methyl ester, and you attach it to a variety of sugars or aromatics, and you begin to see what works and what doesn't. That's experimentation. But one of the neatest ways that I came up with sort of visualizing this during my PhD was looking at the use of the distinctive non-covalent interactions. So you may remember from Gen Chem, end of Gen Chem 1 or 2, where you're looking at the different non-covalent forces. So these are not bonded directly, but they interact somewhat indirectly. So we have pi-pi stacking, we have van der Waals forces, we have hydrogen bonds and also ionic bonds, so generally corresponding to components of our food, like minerals, for example, carbohydrates and proteins, fats, and then also aromatics. And these aren't all of our non-covalent forces. More recently, we've been looking at things like halogen bonding, which is a dipolar interaction, I believe, and also would fit in somewhere around here. But nevertheless, what we can begin to do is create a matrix where we can assess and also look at the different combinations of these things. So most of my work during my PhD existed probably somewhere around here. I was using sugars and long-chain fatty acids. Not soaps, right? We don't have ionics. These are anionic. These are non-ionic, not anionic. And a big class of organogelators, things that gel organic liquids, was also these long-chained sets of aromatic rings and hydrocarbons. And yet we'll see that a variety of these things exhibit the intersection or the juxtaposition of these different properties. And so the cool thing about when you say take something that can pi bond and can form hydrogen bonds is that these things will preferentially come together in solution in a kind of, I like to call, like assembles like, right? You're not going to have, well, it of course gets more complex than that. You can have interactions between rings, for example, and salts. Nevertheless, yeah, this is a good basis for coming up with neat and perhaps new materials that do old things in different ways. Our goal, of course, was to use bio-based materials to make these. And so while some of these, for example, well, it depends. You can make soap from natural oils, obviously, but a lot of the industrial products are made using petroleum chains that come from petroleum, and so the goal was to sort of perhaps supplement or add to that. Anyway, this was a guide to how we would come up with the chemicals, and we'll see in a second how we actually build up more complex chemicals. So the goal here was to create a monomer, and when we think of polymers, we often think of covalently bonded species in a series or in parallel, I guess. Here we were looking at very small monomers that would build up not in covalent bonds, but in this case, non-covalent bonding. So we have these kind of weakly bonded or relatively weakly bonded architectures, which you can grow into fibers or different shapes depending on the solutions you start with and concentrations, and then also what you're made out of. What you can take away from what we have here is we have a small molecule, relatively, made up of distinctive pieces. So here we have a long fatty acid chain, and we can vary, say, the number of carbons in there. This would be coming from fats and oils. We're also going to have a rigid sugar core, in this case primarily doing some hydrogen bonding. And then also, last but not least, an active, quote unquote, aromatic head. So in this case, different substitutions from natural products will give us not only perhaps the ability to pi-pi stack, but interactions with light, importantly. So we could imagine that we have a wiggly piece, a very strong piece, and then something that's doing something. So sort of using these three different components, as we saw, comparison to the two that we were looking at before. And these, as you can see here, could be programmed or tailorized. And we can see, right, again, that we can get each of these components from natural lipids, carbohydrates, and then also lignans or other places as well. And so we'll find that in looking for sustainable resources for creating these materials, we want to make sure that we have platforms or streams to pull them out. We don't want to just use incredibly active molecules if we can't source them readily or easily. So an example of this work that came to, this was a collaboration with, I believe, Andy Brenning, part of Compound Chem, who digitized some of my work. In this case, we took, say, sugars from raspberries and then combined them with fatty acids from waste products, and then turn them into these ester compounds where we were able to swell and then also gel oil. So the premise here is you create sort of like a sponge, and then the oil gets trapped. Those are the dark beads. And then you could, in theory, distill off the oil and collect it. But the premise at this point was just to get it out of, say, an oil spill or an area like that. And so this really looks nice, but it's not perhaps as practical. You're not going to extract a lot of sugars from your raspberries just to make something to clean up your oil spills. I would hope not, though it is possible, right? There's a lot of other good uses for raspberries, like baked goods, for example. And so now the question isn't sourcing things to make valuable materials. It's sort of how we actually make them, right? The difference between the destination and the journey, you might think. So in this case, we're interested in how we get there. And so a popular branch of, I'm not going to say that, a popular thing nowadays is to use mechanochemistry, which is to do actual chemistry generally without solvents and at low temperatures, essentially by mixing, as you can kind of see here in this ball mill. And so we do this as well with things like biodiesel, a source of our lipids, and what we're able to do is to take that gellant and mix it up without heating it at all. And the neat thing is that it's kind of like making Jell-O in a rock tumbler. So typically you would heat and cool Jell-O on the stove, which is great for Jell-O, works very well. But now imagine that you're, say, trying to get a fuel, right, to become a gel. You might not want to heat it for many reasons. Similarly, it might just cost a lot of energy. So in this case, we found that you can mix these up and make rather beautiful fuel gels from biodiesel, and essentially less than 1% of that gellant that we were talking about before, right, that aromatic, that sugar, and then that fatty acid tail. It's cut off here because it's a variety of different tails all coming from whatever was used to make that biodiesel. That's going to be a combination of used cooking oils and other things that were collected and transesterified. And we can see here relatively nice translucent gels. Also, I was trying to filter this gel for some reason out of that grinding media, and you can see it's not dripping. This was over, I think, a period. Is that an actual video? Yeah, nevertheless, nothing happens, right? And so I guess we can see how we make these sustainable mixtures, not only at lower temperature, but in safer means. And then we look at the properties. So in this case, we were interested in studying the gel that we had made to see if it perhaps is useful in any other way. And so I won't go too much into the rheology, but I did want to show a little bit of data. In this case, we have both the G' and G" moduluses, which is going to represent, in this case, the elastic and the viscous. So sort of like the solid-like and liquid-like. And so we're going to take a ratio of these two. The black line in this case represents the elastic modulus and whether it is solid-like. The white squares are going to represent the liquid-like or viscous modulus. And you can see that there's a point in each of these curves which I'll get to in a second, where they cross, meaning that we are going from something more solid to something more liquid. This represents the gel to sol transition. So just like if you've ever had, say, a piece of Jell-O in your mouth and it begins to become watery over time, it's heating up and melting. Another alternative is really anything like butter, for example. It's really hard and then you mash it up and it becomes soft. That's going from some sort of emulsion or gel state to the liquid state where it flows. And this is why it's so important, right? We don't want fuel that's been spilled outside to flow. We want to trap it, transport it, and then do whatever we want with it. Make it flow if you need. And so the neat thing here is that we started with a solid. We ramp up the strain, so we strain it more and more until it turns into a liquid. And then if we let go for a little bit, about 60 seconds in between, we can see that the solid comes back. And then we break it up again, we turn it into a liquid, we let it sit, and it resets and becomes even a little bit stronger, as you can see. And so what we found is that we have a material here, kind of like your ketchup, where if you let it sit in the fridge for a while and try to pour it, nothing comes out. You have to bang on it, right? Apply some force to create some shear, and then you're going to have it pouring out like a liquid. Here we could imagine a bio-based fuel that could, for example, be a solid. So if a car tipped over and the fuel tank cracked, it wouldn't leak out. But when you need to press it through your engine or system, you could apply a little temperature or a little shear and then get out a nice liquid fuel to use. Might be really neat with, say, snowmobiles on research missions where they're going to places where you don't want, say, a lubricant or fluid to spill onto the ground, or even a fuel in that case. And there's a lot more cool rheology to do on this stuff. This was the latter half of my thesis. And so if you're interested in sort of the bounds between chemistry and synthesis and then also chemical engineering and application, this is a great way to become involved in that. More recently, what I've been working with is coming up with other emulsions and formulations, generally things related to cosmetics and personal care products, not only from locally sourced ingredients, so these are going to be either oils that are relatively local, or components, for example, like lignin from, say, the trees nearby, and then also including a variety of non-food additives. You can see on the right an example of a soap we had made that's really foamy that uses guar gum, which can be eaten, so you'd rather preserve it for that, versus, say, something that's been made with methyl cellulose, which can be made from waste paper products and other processes, and so isn't edible and doesn't sort of compete for providing nutrition to us. And so we might say want more of that, but we can see we have a little while to go. Here we have a lot of foam on the left and not really as much that stays on the right. This was about over a week. The emulsion began to settle. So how can we improve upon that without taking away food from people? Lastly, the goal is always to make them simple and easy to use and make, and so in this case, safe. That's one of the aspects of this, and so we'll be using those mechanochemical or mechanophysical processes here as well. Okay, so we've done a brief introduction into how we upgrade the biomass and then how we make functional materials. I didn't go into depth into so many things yet, like, for example, how we choose ways to apply the functional materials, all the kind of vetting that goes into when we make these molecules, proving to everyone that we know what they are and they're doing the things we expect. But let's just take a moment to step back a little bit and look at how we critically evaluate these projects that we do. So we won't look explicitly at the science evaluation, we'll look at the big scale metrics through what is known as life cycle assessment. And I always love to intro this topic by talking about something we're not doing right now, but imagine you're going to a meeting with a group of people, and of course you need a cup of coffee. Simple question would just be, which of these 3 cups would you choose? Would you choose a paper cup? Would you choose a ceramic coffee mug? Or would you choose a styrofoam cup? And you can take a moment to think. You probably have your own answer. Maybe you have a favorite mug. Maybe you love talking to the guy who sells you the coffee. Maybe you like the quick and easy styrofoam cup. Whether or not you have your personal preference. Now we have sort of more of an average of what is the most sustainable. So take a moment to think about which of these options is the quote-unquote best when balancing a variety of things like where it comes from, the materials that are used, its cost. People might shame you, right, if you're using a petroleum-based styrofoam cup, perhaps, or they might love you if you have a really cool thing on your mug. And so take a second to think which of these you would choose, given sort of a random or everyday scenario. And so it turns out that the best option, as long as you wash it 50 times, which is something we didn't even think about, is going to be your ceramic mug. Generally, I think it's something like over 100, and you definitely used all of that energy in the sourcing of materials versus, say, something that could be recycled, but is probably one use, and then also something that's one use and arguably can't easily be recycled. So there are people who actually balance these economic considerations or the cost, the social constructs or implications, and then also environmental impacts to come up with sort of the most sustainable option, and that's what we'll be doing with our LCA. And know that there's some good research on sort of like what's better, a paper or plastic bag, with these mugs as well. So that's where I got a little bit of this data about the 50 times. So now let's sort of learn how we can do this with chemicals. So we're going to do a brief introduction to life cycle assessment. And so in this case, the good news is you only ever really have 3 steps. To do the assessment itself, there's always some sort of evaluating afterwards. And so in this case, you're going to not only list all of the materials in your system, however you're defining it, you're also going to map the ways that they flow. So we're going to see how they interact and what doesn't interact. And then lastly, we're going to use our critical thinking skills to judge the safety of whatever it is we've done. And if you've ever taken an intro science course, you've probably had to do some form of a pre-lab when working with chemicals or biological reagents. And it's really the same exact thing. It's a fancy Org 1 pre-lab, right? Where you list out all the chemicals. Sometimes you have to draw diagrams of how they flow together. I remember we did that for extractions. It was really helpful. And then lastly, you do a little bit of a safety thing, right? Is this reasonable to do? And then really the last step is to judge, bigger picture is the sustainability. And that's almost impossible to do perfectly. The goal here is to balance, right, cost, social impacts, and environmental impacts. And there are, of course, other metrics than cost. And so just to look at the kind of metrics that we'll use, we're going to look to calculate something regarding the efficiency of how you make your product, the impacts of the energy that you're using to do the process in this case. So could be CO2 emitted per kilojoule or kilowatt hour that you use. And then lastly, there are always going to be social impacts. These are generally the hardest to classify, not only because you would need to study large groups of people to get a representative average, but you never know how people are going to respond as well. They might love or hate a product. Just because it's sustainable doesn't mean that it's socially acceptable, or just because it is efficient doesn't mean that it's good for people. And so we'll look at all of these ideas in a different example. And so just to explain what we do after we make that list, we map that flow, and we begin to judge the safety of what we're working with. We do that last one by looking at the toxicity of the different chemicals that we use and what could escape into the environment. And so we create what is typically known as a multi-component model, which is a fancy way of saying a model with multiple components. In this case, water, air, soil, and sediment, the latter two being distinguished by whether or not it is more or less organic content. So soil, which fosters life, is going to have more organics, and sediment is going to be more rocky and inorganic. And so we can create different systems if you say live right by the water or in the water versus a generally arid region, or perhaps just sort of a general area. And just to point out, all of these are available at KU ScholarWorks, these methods to be used for a variety of different undergraduate contexts, for example, doing student research, doing online labs, for example, and so you can take a lot of this data and play through those. There's specific calculations, which I won't be going through today, but also a guide as to how to use all this kind of stuff to look at your work as well. If you have 2 papers with different methods, you can use these to compare and analyze them. The more data, the better, but 2 is a good start. So let's talk a little bit more about some of the metrics that we use. In this case, we're going to be looking at the synthesis of aspirin. So we're going to be doing sort of a simpler LCA, sometimes I call it an LCI, where we're looking at, say, the efficiency of the reaction, kind of like a yield. We can look at some of the economics, which can often be closely related to the energy that's going in and out. In this case, I guess a specific energy. And then also we have the relative toxicities, not only for individual people, but also for large-scale effects like acid rain or pollution. And these are the ones that I use. I like to break them down into those kind of 3 general areas of process, product, and people. That's Marcus Labonis's tag phrase, not mine. And we also have a variety of other metrics that you can use. So know that not only are these open resources, but they're tailorizable. So if you want to do an environmental look at, say, nitrogen or phosphorus flows, or if you're in the bio world and you want to look at some of these, that works too. So let's do an actual case study. Let's talk about making aspirin. So in this case, what we're going to do is look at kind of the theory of what goes into making a molecule and then some of the potential real-world impacts. I will note that a lot of these analyses are relatively rudimentary, but they still use actual data. So they'll give us some insight, but there's always more to be done. There are more rigorous methods to do comprehensive LCAs and also TEAs, techno-economic analyses, which we won't get into today because we're thinking open courses and software. So to compare different aspirin syntheses through an LCA and kind of evaluate the sustainability and safety, we're going to need to look at some data. And so in this case, we're going to take data from a couple of different sources. First are going to be 4 different procedures to make aspirin that are used in the general chemistry laboratory. And you can see they're each a little bit different. They each have a different catalyst. In this case, calcium carbonate versus pyridine, which is basic, versus sulfuric acid, which is acidic, strongly acidic, and then also phosphoric acid, which is going to be weakly acidic, so a variety. We also have a microwave method using, I believe, a traditional household microwave versus a microscale, which is to say a much smaller scale than gram scale. So teeny, that was popular in the, 80s, 90s, even today. And then we're going to compare this to an actual industrial synthesis, which is interestingly not catalytic. We often think of catalysis as always a step above stoichiometric reactions, but we'll see that they got their efficiency and yield pretty high. And this is going to be from a mid-century process, so I think it's from around the early 1950s. And we're going to compare all of those. So the goal here is that we have the same product, which is acetyl salicylic acid, that's aspirin for us, and yet we're going to compare these 5 different methods using the same metrics, and we'll sort of look at those. Now to do this, we're going to need a couple of pieces of information, for example, things like densities, in case a procedure mentions something in liters and you want it in kilograms. We're also going to look at fundamental properties of some of these reagents going in. We don't know what those are yet. We won't actually look at those today, but we know that some of them must be relatively similar, but also in different amounts. We're also going to take costs from a variety of different sites. For example, there are pricing indices online. They're generally hard to access. So what I like to do is to go to 3 competitive websites, places like Sigma Aldrich, Fisher Scientific, Thermo Fisher, and I price out relative amounts and then come up with an average that seems reasonable for a sort of small bench scale or gram scale synthesis. Obviously, if you're buying kilogram amounts, it's going to change. So if you're looking at engineering impacts, this is not going to be useful for cost. This is best for cost per gram, I would argue. We'll use also stuff straight from the MSDS, so those are all free, and you're going to be able to get LD and LC50s, which are going to relate the dose and the concentration that's considered lethal. We'll look at toxicity with that in a moment. And then through some of the chemistry literature, there's also good data on things like acid rain potential and ozone depletion potential and things like that. And so each of these different sets of numbers are going to correspond to a different metric that we're going to come out with. And if you weren't ready for enough information, let's just jump in a little bit easy. So here we're going to compare the first 4 academic syntheses to a 5th or industrial synthesis. And I've colored these. Generally red is the worst or most impactful, least benign. And number 1 is going to be our best, and everything in between is going to be yellow. So first let's look at what's called PMI. This has to do with the efficiency of a reaction. So unlike yield, where you're only looking at your product, here we're going to look at everything that goes in. And so in this case, we can find that number 2 uses quite a lot of reagents compared to, say, the amount of product that you get out, whereas, no surprise, the industrial process is relatively efficient. But we can see that, say, that microwave process is almost as efficient. And so maybe it's impractical to do a industrial scale reaction in your undergraduate lab or wherever you're making your aspirin, and so you might be able to use, say, some of these methods, or at least distinguish these between others that are most inherently wasteful or least efficient. So let's look at some other metrics as well, and again, you don't need to understand each and every one of these, but in this case the goal is just to see how we can use different metrics to sort of clarify where we might choose our synthesis from or why. So looking at cost, it does seem like that microwave reaction is the least impactful. Interestingly, when we look at the potential to form smog, or in this case emit volatile organic chemicals into the atmosphere, which will then help form smog, we can see that the second one, this microscale, is still not our best. And then in this case, we can also see that our industrial is still our best bet. We also note that there are 2 missing areas of data. This could be because, in theory, they don't commit to the smog formation potential, or that we just don't have the information to calculate this. So what I love about LCAs are that they really help pinpoint the areas where new data needs to be found. Maybe we need a better method for calculating the smog formation potential, or maybe we also need more data just so that we can calculate it. But bets are this might also mean that it doesn't impact it. And so we have to better look at some of the data that comes from our table. Last but not least, we can look at, say, an estimation of the global warming potential, which is coming from the energy, so how much energy was used per reaction, and then we can take an average of how much CO2 is emitted based on where you get your energy from. And so in this case, we can see the microwave, though relatively efficient in terms of mass, is relatively inefficient in terms of energy. And so what we might find here is that perhaps using an actual microwave reactor rather than a conventional reactor would be a good step, but it's no surprise that this probably wouldn't scale industrially, at least not using these methods. You probably need something a little more special. And the other thing that I love about these is rarely, if ever, is one synthesis going to be the best. So in this case, we can see that even though number 5, the industrial reaction, is well optimized to be least wasteful, least polluting perhaps as well, and most energy efficient, we find that there's still an improvement that could be made based on perhaps including elements from this microwave synthesis. And so we can think about that, right? Maybe we're going to pick and choose a variable to change, say based on synthesis number 5 or 1, and so we're going to include these different things. But we can begin to compare all of these based on just the data from the methods and then also some of these other things. And so the next step is generally going to be to come up with best suggestions and best practices, but also to sort of change one thing and then go, right? So iterate the differences in the different procedures that you're going to try. And at least, even though under certain circumstances your procedure might be the best, if you weren't worried about cost per se, that's a really lucky consideration. Maybe you might choose something like 4, for example, that doesn't have very high emissions, but can be done on a lab scale relatively easily. And so educators can also use this to not only choose perhaps the safest, but most sustainable, right? Balancing, say, things like cost and things related to pollution, and then also comparing sustainable ideas like how efficient something is over time, and then also the amount of CO2 that's emitted, right? So we can see lots of different cares and concerns, and it's great for students because rarely are they going to come up with the same answer. They're going to need to think their way through why something is perhaps the best choice or not. Some other of my current work, now I'm doing a little bit of environmental teaching and research as well, and so this is a bit of a pun, but I'm working with Beyond Benign on looking at, say, the flows and pools of certain chemicals. So here what we do is we take different pools. For example, we could break them up between the spheres on Earth, and then imagine that certain chemicals sit in these. We come up with a cycle. You may notice that all of these are balanced and the entire reaction is balanced, and so we can come up with sort of a one-step reaction where things are flowing through the system. The pun here is that it's current work because we're looking literally at mass flows and charge flows, or currents. And so this may help us sort of better understand how natural systems, which are generally not balanced over short amounts of time, are going to respond and react to perturbances and other things like that. And yeah. So that was just a brief introduction to some of my research, talking about some of the more traditional experimental research I do on how we make safer chemicals, but then also the methods we use that are hopefully more sustainable, and then how we actually prove that something's green, right? It's not just enough to say, for example, oh, mine's green because it has a catalyst or it has less solvent. We need to show this, and so we develop educational tools to help analyze and look at sustainability with different metrics. Feel free to follow me on Twitter. I'm at HeteroCat. I used to do a lot of heterogeneous catalysis, which led to this horrible username. And you're always welcome to stop by in the future at Manhattan College or come reach out with any questions or comments. And yeah, let me know how this first one went. Hopefully you guys enjoyed it, and I'll be back later today talking a little bit about the difference between atomic mass and molecular weight. So don't hold your breath, and I will see you until then.